Let's solve some problems on standing waves. 15a, describe a difference or state a difference. Well, there's many differences between standing and traveling waves. You can talk about how traveling waves transfer energy through a medium, but standing waves don't, or anything else we've studied. Part B, they're asking us to draw a representation of the displacement of the air in the pipe at F1 and at F3. Particles at the left edge, they cannot be displaced because if they try to vibrate left and right, they bump into the wall. So they have no displacement. Particles at the open end are free to move, so they go really far left and right. This is a node here. This is an antinode. These particles at the left edge will go positive displacement, but they'll also achieve big leftward displacement or negative. So when we draw the sine curve, we can draw the curve going up like this, all the way to the end, but then we could draw the dotted line, which shows the other half of the oscillation. The particles go really far positively and really far negatively. The third harmonic is the same thing, but instead of stopping, we start at a node on the left edge, and we have to have an antinode at the right edge. But instead of stopping at this antinode, we're going to put this much of a wave onto the pipe. So we take that shape that I just drew in purple, you stretch it out across the pipe. And then we can draw a dotted line showing the other half of the oscillation. The particles here at the edge, again, will have a really big negative displacement, but they'll also reach really big positive displacement. Prove that the ratio F3 over F1 equals 3. Now, you can look at your picture and realize that the length here contains 1/4 of a cycle. So distance, in terms of distance, the length is 1/4 of a wavelength. And you could look down at the bottom and say, well, hey, here I have almost 1 full cycle. How much do I have? 3/4. If you don't want to go through this process, you can instead memorize the equation. N, the harmonic number, times lambda n is equal to 4L. And you can say, for the first wavelength, lambda 1, I have 1 times lambda 1 equals 4L, or simply lambda 1 equals 4L. And for the third here, the third wavelength, I have 3 times lambda 3 equals 4L, or lambda 3 equals 4L over 3. So how do we take these lambdas and convert them into frequencies? We have to use the wave speed equation. C equals F lambda, or if we divide both sides by lambda, we get, let's try this again. Dividing both sides by lambda gives us frequency equals C over lambda. So F1 is C over lambda 1, which is 4L. F3 is C over lambda 3, which is 4L over 3. The 3 down low is a double denominator, or we're dividing by a fraction, and it comes into the numerator if we work out the math. So now we just have to take the ratio, F3 over F1, and we have 3C over 4L divided by C over 4L, which is 3. State in terms of the boundary conditions the reason why the ratio of higher frequencies to that of the fundamental, this is another name for F1, must always be an integer. As soon as we see in terms of the boundary conditions, in terms of, that means you have to describe the boundary conditions for this pipe. So what do? The first thing we do is at the closed end, there must be a node, because particles can't move. And at the open end, there is an antinode. And the reason that we'll give, this is not a complete reason, but it's a partial reason, because the particles are free to move. Free ends always turn into antinodes. And that's not something we've really proved, but we saw a video at one point with the string, and we sent a pulse through, and it was free to move at the edge. And when the pulse reached this edge, the edge went really high and really low, and that kind of demonstrated this property. Now, if you turn back to the answer, this is actually enough for the point. They didn't require any explanation, and the reason is because it says to state. But if they had asked us to explain, and maybe if they had made this worth 2 points instead of 1, we could then go on to say, so only odd integer multiples of lambda over 4 will fit, well, let's say will satisfy these boundary conditions. That's how we would do the full explanation. They didn't require the second part because we were only asked to state.